without H in front, I think.
Without
H in front.
That's true.
Yeah. So we'll see. We'll see. Well, in the afternoon, we'll take the H back. But this morning we take H off from QCD. So
but I have D instead of H.
You have D. Okay. Well, we have a T QCD today. Alright. This is what Chihiro, everybody knows Chihiro. She's going to talk about some recent developments which will certainly have something to do with the attempts by, let's say, hQCD people. In other words, it's an issue of scalar method.
Thank you. Good morning, everyone. So I thank WCU organizers for the invitation, and I thank all of you to be here for my seminar. I'm always happy to be here and to see all of you. So what I'm going to talk about is a very fundamental question: origin of happiness, and how to model it in terms of the language of effective chiral languages. So most of my talk is based on the work with in collaboration with hQCD, and Chihiro. And very end of my talk, I also like to show some tentative result, which is a phase diagram. This is the work ongoing study with Igor Nishesty in Frankfurt. So let me define the problem. So QCD Lagrangian, this is the top part of the origin QCD Lagrangian, has an approximate chiral symmetry. Particularly, this is a symmetry in right quark up and down quark sector, because the bare quark masses are much smaller than lambda QCD. This is a typical scale of Strohm-Lupin. And this symmetry breaking term is supposed to be safely negligible. However, this chiral symmetry is not manifest in hadronic spectra, because we don't see any degeneracy in masses of party partners, like masses of between scalar, pseudoscalar, or between vector nets or vector particles. So this is our knowledge. So essentially, the splitting between those two party partners is the signal of dynamical breaking of chiral symmetry. Okay. So this partly explains the origin of hadron masses, namely the bare quark gets dressed. It has a cloud of gluon and quark and anti-quark pairs. And the small bare quark mass becomes enlarged and is called constant quark, and constant quark masses around 300 to 400 MeV. Then this intuitively explains the proton mass, for instance, which is much greater than the sum of current quark masses, which is at most 15 MeV. So we have a scale, the hadron mass. This is the scale in QCD because of the dynamical breaking, spontaneous breaking of chiral symmetry. So the scale in QCD, so go back to the QCD Lagrangian. Taking chiral limits, the QCD Lagrangian has no scale at all. So QCD Lagrangian, QCD, this is approximately conformal invariant theory. So appearance of scale is also related to the breaking of conformal invariance. So QCD is known to have anomaly, conformal anomaly or a trace anomaly. So this is a current corresponding to the scale transformation, and when you take the divergence of this current, is not equal to 0. And this is actually equal to trace of energy moment tensor, and QCD it's expressed in terms of gluon composite operator plus quark composite operator. So hadron masses are supposed to be some combination of basically those two composites. So the first one is directly associated with spontaneous chirosymmetry breaking, and another is something not related to spontaneous chirosymmetry breaking. So the question is how to determine these composites. Of course, it's a different task because hadrons are a relativistic system and very strongly interacting systems. So what to do? So my strategy is to use chiral effective Lagrangian approaches constrained by symmetry requirements in QCD, assuming well-defined quasi-particle description for mesons and baryons everywhere.
May I ask some question? So you say that the possible origin of the hadron mass can be classified into two things, but then spontaneous chirosymmetry breaking.
Yes.
The one is kind of chiral trace anomaly.
Yes.
But
so this is exactly my issue. What it is.
Yeah, but my feeling is that these two things might be related to each other.
Yes, they are related.
They can be given in terms of hQCD. So can we divide the problem into two things? Okay, maybe.
Yeah, for instance, when the chirosymmetry is restored, this is precisely zero. So the question is whether you have non-vanishing
even
mass.
in the chiral symmetry restored phase, we might have some mass. Oh, I see.
So the question is nuclear mass or other hadron masses, meson masses are going to zero precisely or not. So mesons in chiral broken phase.
Chihiro,
Yes.
let me ask you one question, and I guess that maybe most of the intuition is coming from some kind of a GOR relation. But apart
Which
from the
relation?
GOR relation, which
Gamma
relates
box.
the measured mass, ion mass with the Q. But apart from the ions, is there any such kind of a general relation?
No.
So why do you think that the chiral condensation itself can control the measured mass? If pion case, for pion case, it is a kind of pseudo Boltzmann boson, so it is reasonable, and it is controlled by
Chiral
mass
symmetry.
and chiral symmetry. But for other hadron mass, you are
Right.
talking about the general hadron mass, right?
That's right. That's right. For instance,
So-
vector meson masses.
So what is the and the reasoning that you want to relate all the hadron mass?
There is no justification.
No.
No. It depends on its model dynamics. So what's the requirement from the chiral symmetry is that, okay, so suppose chiral symmetry is restored, and then scalar meson mass should be zero because it's considered to be a chiral partner of non-Boson boson pion, and the pion is massless everywhere if the chiral symmetry is spontaneously broken. This is protected by chiral symmetry, non-Boson theorem. So MS becomes zero, okay, that's fine. But what about other mesons? So the chiral symmetry requires, of course, two masses. That's the splitting of those two masses should be zero. So this is the requirement for chiral symmetry. But the mass by itself, it's not controlled by the chiral symmetry. And actually, if you want to calculate the temperature dependence or density dependence of those vector meson masses in terms of some chiral Lagrangians, and in some model predicts it goes down with increasing temperature or density, and some other model predicts goes up. So it depends on the model. But instead of those model independent description, we would like to have some general argument as much as possible. So there is an argument by Weinberg. The idea is called Mendix symmetry. So this is algebraic consequence for pion scalar rho meson and axial vector meson, those lower lying mesons, they are classified by irreducible representation. Those irreducible representation either under chiral symmetry transformation in broken phase of chiral symmetry. So S stands for singlet, A stands for adjoint. So of course its argument is based on some assumptions, current algebra and corresponding low energy theorems on scattering amplitude for pioneer scattering and large MC arguments, and also Regge trajectory, some requirements on mesomass square matrix. So the prediction of the magnetic symmetry is that rho mesomass is almost equal to scalar mesomass. So this is not very bad. So of course, scalar meson, what is scalar meson? This is always problematic. It's still under debate. But when you go to a particle data graph, the mass is roughly 600 to 700 MeV, and rho meson mass is 770 MeV. So this relation is not very bad. And what's the further consequence? What's the further prediction of magnetic symmetry when chiral symmetry is restored? So this is that all meson masses should be zero. Not only rho meson but also A meson should be zero. So as I said, we expect that scalar meson mass becomes zero when chiral symmetry is restored. And the magnetic symmetry dictates this is equal to rho meson mass, and rho meson mass will be degenerate with A1 meson mass, and this requirement means A1 meson mass also should be zero.
I have one question. So why all meson should be massless at chiral distribution point? Because chiral distribution point biomass might be massless. So requirement is general.
No, I'm talking about, so I consider the limiting cause a limiting situation. We approach chiral symmetry restoration point from below, from symmetry broken phase. And in symmetry broken phase, pion mass is zero always in the chiral limit. From harmonic wall. Okay, so this is massive, but it approaches zero. And this means rho meson mass should be approaching 0, 2, and A1 meson as well. So this is his argument.
So why the isospin, different isospin multiplet has the same mass? Is there a first reason? Do you understand?
When isospin,
or here, because of different spins, the claim different spins.
so they are longitudinal component of rho and A.
So why, I just don't understand that, there are certainly measures can be in different irreducible representation of non-abelian chiral, right?
Different from?
Yeah, they can be in different, there are many different multiplets,
Yeah, that's right.
which don't mix, right? Different irreducible representation means they don't mix, right? And so,
Different
may I understand
reducible
why, the rho meson and the scalar meson has a different, the same mass?
So rho meson and scalar meson, they are classified with the same eigenvalue of mass matrix square.
So FIAS rho A1 is some superposition.
Yes.
Say again?
So this, that
That's right.
FIAS rho A1.
So
It's
ion
superposition
state,
of irreducible
some coefficients.
That is the same.
Plus some other coefficients of so adjoint, singlet, plus singlet adjoint. Okay, and similar to for axial vector methods.
So you are saying that the different reducible representations are mixing under this Mendel symmetry.
Yes,
Is that correct?
yes.
So what is this Mendel symmetry?
Or read it. I would suggest that.
So
Symmetry is probably even if we are in symmetry breaking phase, we can
That's
still
right, that's right.
classify particle using the irreducible representation of chiral symmetry.
Right.
Even if
So-
we are
it
in
is broken.
Yes. So in general, if the chiral symmetry is continuously broken, hadronic states are considered to be very complicated superposition of reducible representation. But the Mendel symmetry tells us that they are, at least those low-lying mesons can be classified by those four irreducible representations. So in this sense, the algebra is closed.
Well, there's a few assumptions like Reggie asymptotics and so on and so on. For algebras
So this is not purely, I guess, current algebra.
No.
Real algebra.
No.
There are further assumptions which are in there.
Right.
RGNC and Reggie trajectories and things like that.
So it's misleading, I would say, that the just maybe it is irreducible representation doesn't mean that real algebra is irreducible representation.
It's like
So Mendel symmetry is not. Is this a real algebra symmetry or
Yes,
it's
yes.
different?
The algebra.
No, you have a representation of various symmetry representations, and you have a algebra associated with it, and that algebra is very closely related to current algebra, like other bicycle relations. Yes, they are all related. Now, however, within that set of relation, he imposes further conditions like RGNC and Reggie asymptotics and things like this. And with that condition, he shows that there is a mass matrix which can be degenerate certainly. And that's what means what he is.
So the algebra on top of those assumptions or requirements reduces, it's reduced to be this line. So this is basically his claim.
Maybe I should read it.
Yeah, no, I suggest that you read it. I mean, this is I'm surprised that the applied physicists are not reading this particular paper. I don't understand it. No. This is a very.
I know.
I would say it's a very well-known thing, but it's not read very much.
Yeah, but it's no textbook, standard textbook.
I mean, we only read the standard textbooks.
Yeah.
I read a lot of other things in the textbook.
Many of us are not educated.
No, it has nothing to do. You're very well educated, but that has nothing to do with education.
Yeah, so but in any case, I will not use this medicine. I simply, I list it because it's existing, but it's not known.
One more short question. So, MRO, most of the low meson is degenerative parts.
Yes?
So, part that is important when we discuss nuclear force.
Yes.
So, the difference between omega meson mass and sigma meson mass is very
Oh yeah, that's right. Oh, but it's not the same. Yeah, okay.
Yes, sure.
But this never applied to another. So okay, so what are baryons? So just for an illustrative purpose, let me start with the standard Gelman-Levy model. So the question is how to emerge a nuclear mass star. So the Minesimum Lagrangian is given here. Nucleokinetic term plus interaction term. Explicit mass term is of course forbidden because we impose chiral symmetry or invariance. And once the chiral symmetry is spontaneously broken, this sigma field has non-bidirectional expectantial values, and this becomes essentially the nucleon mass. So it's proportional to, directly proportional to sigma condensation. So this is sigma expectantial value by itself, the order parameter of chiral symmetry. Okay, so what is implicitly assumed here is that chiral transformation for a nucleon is just the same as for a quark. But this is not really clear or really clear why it should be so. Because nucleon is a composite object made of three quarks. So what about nucleon mass when the chiral symmetry is restored? Well, this Gaiman-Levy model tells us that nucleon mass should be zero because the entire mass of a nucleon is just generated by spontaneous chiral symmetry breaking. So this is so I will call this this is standard assignment, or sometimes it's called naive assignment of chirality to a nucleon field. And another assignment is known, this is called mirror assignment. So with mirror assignment, dynamic chiral symmetry breaking generates only mass difference between parity partners, positive parity nucleon state and negative parity nucleon states. However, at the chiral symmetry restriction point, the generated mass, say M0, this is not necessary to be zero. So here I have listed a transformation property for two nucleons. So the nucleon fields with index 1, labeled with 1, so they transformed in a standard way, okay, under SU2 chiral symmetry. On the other hand, another nucleon field with index 2, they transforms differently under chiral transformation. The point is that, so those handedness, left-handedness and right-handedness for nucleon fields, they are corresponding to helicity. On the other hand, the chiral left-handedness, right-handedness for associated with chiral symmetry, this is a totally independent ladder. So they are in a sense more abstract. Okay, so this is allowed because nucleon is a composite system. Okay, so with this mirror assignment, so this is called mirror assignment, and with this mirror assignment, it's allowed to have this kind of explicit mass term. But of course, it doesn't break chiral symmetry. It's invariant, chiral invariant, and the transformation. And other terms are just standard, same as in standard Minesimum model, plus meson terms, which is responsible for spontaneous chiral symmetry breaking. And of course, in general, when chiral symmetry is spontaneously broken, one has to take a superposition of possible linear combination. So linear combination of standard assignment and mirror assignment and some others.
So could you say again what is the assignment in index 1 and 2 means?
Index 1 and 2?
Yeah.
So
Is it just
I simply
consider-
prepare two different nucleon fields
For what?
corresponding to positive and negative parity states.
Parity.
Yes, parity. So they are not, of course, parity eigenstates, they are mixed. So they are mixed, okay? And as a diagonalization, we define positive parity nucleon state and negative parity nucleon states. So this is determined by this delta, and delta is the function of sigma and M0. And the nucleon masses are given as a function of sigma and m0, and you can easily see that even when the chiral symmetry is restored, namely sigma goes to 0, the mass is not masses are not so that they are not equal to 0, but equal to m0. This is some number, non-zero number. So this is an illustration for the masses, nuclear masses, as a function of sigma condensation. So the upper point, so here, so those 2 points are corresponding to vacuum values for positive parity nucleon, which is the mass is 940 MeV, and for negative parity states, the mass is about 1 GeV, say 1.5 GeV or so. Okay. So there is a splitting, of course, in vacuum because chiral symmetry is broken, and with decreasing the chiral condensate, those masses are getting closer and closer, and finally they are on top of each other. But how large it is eventually at chiral symmetry restriction point, it depends on the assignment, as I said. And the red curves are the result of a standard assignment, and the blue curves are corresponding to mirror assignments. So the question is how large it is, this M0. So this, so you can determine this M0 roughly. For instance, I take the same linear sigma model, nuclear, this is this nuclear system, and negative parity nucleon decays into positive parity nucleon plus ion. So we know the experimental value for this decay width. So from this decay width, you can determine M0, which is roughly 300 MeV. And other estimations are also existing. For instance, if you add axial vector mesons in addition to a pion-nucleon system, and then this, of course, couples to pion, and there's a mixing and so on. And so in the presence of axial vector mesons, you can repeat the same calculation, but the number is different. In this case, the preferred number for M0 is around 500 MeV. And another reference number is coming from nuclear property. So they started with a linear sigma model plus this assuming mirror variance. And then they applied this model to nuclear matter, and they determined, so they treated this M0 just as a free parameter. And then they determined this M0 in such a way that the model reproduces the non-nuclear matter property, like saturation density, incompressibility, and so on. Okay, so, but those numbers are very different. So I'd like to make some a little bit more reliable estimate of this M0 in both.
So are there kind of program? Because I'm not sure if the difference of the M0 between these three papers are really a problem or not.
It's a problem.
But the mixing.
Because the equation of state in, for instance, dense matter or hot matter
I think
strongly depends on the mass of nucleon.
But M0 can be determined by the dynamics. Dynamics.
Yes. Yeah, so different number means just a different dynamics of corresponding
So in
ones.
this sense, I think it's okay to have different numbers for different systems.
Yeah, okay, so in this respect, this is not a problem.
Okay. So what is the problem you want to?
What I like to do is to fix these numbers based on symmetry arguments.
You want to reproduce this number?
No. I like to fix it. So just forget about those numbers.
Okay. Okay, so you want to fix it?
No, wait a second. There is a great difference between 800 MeV and 200 MeV in zero.
Yes.
Because if it's 800 MeV, that would mean that in order to get to 1,947 by 944 nucleon, only a very small portion that goes in there. Okay, so that means that the so-called spontaneously generated mass within that the chiral sector is very small. You have to change the nuclear physics entirely. Nuclear physics will be changed completely because nuclear mass already in nuclear matter is about 20% down. I mean, some 15% down from the free space. So already if you go to a dense metal, it will change quite quickly. So it will change the nuclear physics.
So you mean the difference itself is okay, but it's too big.
No, that's right. This difference is, in that case, if it's 800, then it's too small. The difference is too small. Between 1,000 and 800 is just
So if this is true, only 10% of total nuclear mass is coming from dynamical chiral symmetry vacuum. So this is precisely related to your previous question, how to make a decomposition of chiral masses. Okay?
And do you have any explicit relation between enter and G?
I will give it.
And the H also changes depending on the situation.
H, yes, hadronics. So this is difference represents hadronic states.
I am slightly confused. So for case 1, 2, 3 case where with the pion, with the axial vector. So are you talking about the really different hadron? So or the same hadrons? Or the same variance? What these 3 cases imply?
3 cases implies that so different. So if you so the value of m0 depends on which degrees of freedoms you have in your model.
But you must have some when you introduce this parity relating. You must have in mind some actual variance factors, right? And proton and is a pair is something not sigma or whatever. So when you talk about these 3 cases, so do you mean that you must introduce a different pairing with the protons?
Right. At least you have to prepare parity partners in your model.
So the parity partners are different. Protons parity partners are supposed to be different according to which measures are in the medium. So I'm
No,
not sure whether
we know which state is the parity partner. So this is fixed. So the negative parity partner of nucleon is called N star state, N star 1535 states. So this has spin 1/2 and the parity is negative. So this is a very natural candidate of parity partner of nucleon. Nucleon has spin 1/2 and the parity is plus.
right, but you just introduced one candidate for parity partner.
Yes, yes.
But you have 3 cases.
Right.
So do you have to introduce 3 N stars? Is that what you mean?
No.
So-
Just the same single N star states. But depending on your setup and on your degrees of freedom in your model, the number of for M0 is very different.
Oh, you mean
So this is the situation.
in order to produce the same mass?
Yes.
The same
Yes,
mass of
yes,
N star,
yes.
you need a different energy.
Right.
This is a little bit. Word.
Yeah, okay, so our task is to determine this M0 as a function of these Riemann operators. Okay, so now modeling. So as I said, so we would like to handle the scalar modes. So in vacuum scalar modes, so what it is, this is always a question. So this might be some exotic particle or pi-pi composite and so on. So in order to avoid this problem, one can eliminate these scalar modes. because the mass of scalar modes in any case is much greater than pion mass, so this can be integrated out. Okay, so this is a nonlinear chiral Lagrangian. This is a minimal theory constrained by spontaneous chiral symmetry. And as for nuclear matter, empirically we know that we need a scalar boson in addition to sigma meson. Sigma is a scalar meson forming an awful multiple. Because otherwise, the naive, standard linear signal cannot reproduce the nuclear matter ground state as a stable vacuum. Okay, so the signal models needs to be modified. And what about the situation near chiral symmetry restoration? Near chiral symmetry restoration, we do need a scalar meson because it gets lighter and eventually becomes chiral plasma or pion. So we have to treat the scalar meson and pion on an equal footing. So we would like to make a sort of switching from nonlinear signal model, which works pretty well in very low temperature, low density, and as well as vacuum physics, to the linear signal model, where scalar meson is treated as explicit degrees of freedom. So we can make a transformation of the Lagrangian from nonlinear basis to linear basis, or the other way around, from nonlinear basis to linear basis. So let me start with a linear signal model. So phi, this is a basic variable in linear signal model. This is a linear combination of sigma and pi. Sigma plus I times tau matrix times pi. So this transforms like that under chiral symmetry, under chiral transformation. So let's consider this kind of sphere in sigma and pion field space, and the radius of this sphere is corresponding to pion decay constant. So this is the constraint on the model. So the point, say P, on this surface can be transformed to another point, Q, through chiral transformation. So one can also express in terms of angles, four-dimensional angles. Yeah, you can express those four variables in terms of angles, and the radius is fixed, which is f by pion decay constant. So essentially, they are independent variables are three angles. So corresponding to pionic degrees of freedom. So the next task is to rewrite these equations for sigma 1, 2, 3 as a function of those sigma and pi 1, 2, 3 field. And so this can be done by introducing 2 by 2 unitary matrix. This is parameterized like that into I times I times theta vector. Theta vector means theta 1, 2, 3. Okay, so using this unitary matrix, original Lagrangian, linear signal model Lagrangian, is eventually expressed like that. So this is a well-known form of a Lagrangian. So you can easily see it by making polar decomposition of this original phi field. So sigma 0, this is the expectation value of sigma field. But sigma degrees of freedom is considered to be, so to say, frozen, and you can you can simply forget about that. And then this M0 is replaced to Fi, and U is given here. This contains only ion, and it's easy to see this kinetic term appearing in linear sigma model takes derivative of U squared. And this U field transforms similar to phi field under chiral transformation. Okay, so this is basically the strategy how to have nonlinear chiral Lagrangian starting from linear sigma model. So you can take when you take opposite procedure, then it's possible to have linear sigma model Lagrangian starting from nonlinear sigma model. Okay, so now gluon condensates. So as I said, trace anomaly in QCD is given by the trace of energy momentum tensor. It's proportional to expectation value of gluon G mu mu G mu mu. I simply express G squared. And this gluon composite operator should be evaluated in a complicated vacuum, hadronic vacuum. And these hadronic states are all possible hadronic degrees of freedom, but which hadrons are relevant, it depends on the scale, and it depends also on temperature and chemical potential density, which you are looking at. But this is a very general expression, and starting with this general expression, so two-component gluon condensate scenario has been proposed many years ago. So they...
Chihiro, can I ask you a question?
Yes.
Can you go back to transparency? So usually when you go linear sigma model to non-linear sigma model, the so-called sigma mass is kind of frozen, or
Yes,
vacuum
yes.
excitation value is frozen.
Yes.
And what is happening here when you go from non-linear to linear? So what happened here? Is the sigma field is still finite mass or infinite mass, or what is happening? Yeah, when you go from linear to non-linear, sigma is frozen, right?
That's
so
right.
you compare the shell. Now here, what?
So your question is how sigma mass term appears?
Right.
Information
Yeah,
was
it's
lost.
from-
So how
I don't know whether it's lost or not.
It appears from potential.
Or it appears from potential,
Yes,
which
potential.
is this is you are introducing it.
Yes, yes, you have to
Then
introduce.
it's the same.
Right. Yeah, so for instance, I'm going to introduce dilaton potential into my non-linear sigma model, and after linearization, the mass term of scalar mode precisely appears from this potential for dilaton.
Right.
Okay, so decomposition of gluon condensate. So since, as I said, since this is evaluated in the presence of those mesons and mesons and baryons, then presumably some part of the total gluon condensate carries some information of spontaneous chiral symmetry breaking, not only breaking of conformal symmetry. And so we call the first part is the soft gluon condensate, and another hard gluon condensate. And the soft part is of the MC, and hard part is of order n squared. And on the first term is responsible for it's called the chiral symmetry breaking. And there is an indication from lattice gauge theory at finite temperature, was done by Miller some years ago. He extracted in medium gluon condensation from equation of state, and what he has found is that this thermal expectation value of gluon condensation around the chiral symmetry restoration temperature is not equal to its vacuum value, but it's roughly half of its vacuum value. So this indicates that the soft part is melting away because of chiral symmetry restoration. So, okay, so based on those arguments, we would like to introduce soft dilaton and hard dilatons and corresponding potential. This is potential for dilaton. And we assume that this potential is a sum of potential associated with soft dilaton plus another potential associated with hard dilaton.
Sorry, I missed something. So how this calculation identifies the chiral? How can we decompose G-square soft and?
No, so he didn't decompose. He simply calculates the whole thing.
Okay.
So this can be extracted from epsilon minus 3t.
Yeah. So what do you mean chiral?
So it's possible to define pseudo critical temperature for chiral transition.
Ah,
This is a calculation with the dynamic
temperature.
force.
Okay.
Yes, temperature. Yes.
Yes, kind of summarize what I understood on this slide. So, I mean, the G squared, you have some, formula equation for G squared. And in the right hand side, we have two terms. And can I understand in such a way that the first term is related to the force, flavor sector, and the second term is coming from the gluon sector?
Yes, yes.
That's all.
Right.
And so another question is that, oh, I see. Yeah, okay. So, and another question is that you mean the dilaton means scalar blue ball?
Yes.
Am I right?
Yes.
Okay.
Yes. Yeah, sorry, I already mentioned this. So dilaton is blue ball.
So that blue ball can have two components coming
Yes.
from pure gluons and some.
Yeah, something like
force.
that. Yes. So soft blue ball and hard blue ball, so to say. And the potential, I assume very generally accepted form for constraint from component invariance. And
So you want to consider this kind of Fermion condensation of chiral condensation as a part of the gluon condensation?
yes.
That's the idea?
Yes.
So you don't need to consider then the Fermion condensation separately.
Right. Okay, so this potential is known to be a reliable form to describe a conformal symmetry and its breakdown in vacuum. So conformal symmetry is broken in vacuum because of the lambda QCD. But at finite temperature or finite density, temperature and chemical potential, they also break scale invariance now explicitly. So one can add some additional terms into this dilaton potential. So explicit form is a precise form at finite temperature and finite density. This is not known. But from a dimensional analysis, you can imagine that so there must be composed of those terms, t to the fourth times some coefficient, and mu d to the fourth, or so m. This is corresponding to dilaton mass. Dilaton mass is introduced by taking a second derivative of this potential with respect to corresponding dilaton times t squared and or similar term m squared times mu d squared and so on. Okay.
So do you have any reason why this is soft gluon and the hard gluon's behavior is very similar? You have the same potential type, right?
Yes.
Which means that they behave basically in the same way apart from some constant.
Right, but they have different back constant and different some scale Fchi. And for instance, when the chiral symmetry is restored, the potential associated with soft dilaton must have a single minimum.
Right. So, and how do you encode the NC and the NC squared dependence? So BI has such a dependence.
It's a gluon part flavor.
No. She wants to encode all the information which is necessary there. She wants to reproduce, if I understand correctly, she wants to reproduce such NC dependence in terms of this potential difference, right? So your BI or maybe KI or whatever has all such information.
Yes,
and,
we implicitly assume that all of them have NC dependence, but how? This is not known.
So BI has such NC and NC squared dependence.
Yes, it must have some NC. It's
And
different
that is
dependence.
assumption. And so unless you have some phenomenological, so the only thing which is different to me from old and new and linear sigma model is in old days the potential is by hand, while here potential is suggested by conformal symmetry breaking pattern.
Yes.
And okay, so that is the only. There is some motivation.
Yes, exactly. Motivation associated with symmetries.
I'm slightly confused about the last statement on this slide. So, in some cases, even in the presence of temperature and the chemical potential, trace of the stress energy tensile can be zero in some scale. For example, n equals to also theory, even in finite temperature and finite density, T mu can be still zero.
Yes.
So we have some scale, but this does not necessarily mean that T mu have got some finite number.
But in hQCD, this is not the case.
Maybe the coefficients A, B, C, D are zero.
Yeah. There is some
Well,
particular.
Yeah, there must be something like that.
Okay. So.
But in QCD, within QCD, it's always broken.
Yeah, in that case,
So-
of course, the dimensional.
so there are three-
And also, it's quite natural to do this
Right.
hybrid.
So the temperature, for instance, which is much greater than lambda QCD, we have the temperature as a single dimensional quantity. So this breaks very conformal values.
Do you need conformal invariance in addition to scaling invariance? They are not conformal invariance and scaling invariance. Conformal invariance includes scaling invariance.
Yes.
And did you use
Scaling values.
Scaling.
We have enforced. Okay. So I have put a lot of equations, but what we have done is not very complicated. So let's have a look just by step. So let me start with a very general nonlinear sigma model. Okay, nonlinear sigma model for pion. I consider at the moment only pion as mesonic field plus nucleons denoted by psi. And now I introduce soft dilaton, chi-S, by imposing trace invariance together with chiral invariance. So the original nonlinear sigma model has the mass term for nucleon and for nucleon over constant Bock mass term plus a kinetic term for pion fields. So I have two dimensional quantities, mass of fermion and pion decay constant square. So that's why, so in order to maintain scale invariance, chi S field appear in those two terms. Okay? And I have introduced some new parameter kappa. This is the ratio of pion decay constant divided by some new scale associated with chi S. Chi S appears here in the population. Okay. And plus Lagrangian, this is a kinetic term for chi S plus potential. Okay. So you can easily get the second one. So this is a simple algebraic calculation. And A and V, so curly A and curly V, they are given by pion fields, some combination of pion fields, and the dilaton potential. So now, at first sight, it looks different from the previous form, but when you identify the back constant associated with soft dilaton is equal to the product of soft dilaton mass square times F chi square, then you can easily see that this is just equal to the previous standard form. Okay, so this potential is just very standard. Okay, now I would like to make linearization. I introduce a new sigma field. So this is a combination of scalar field, new scalar field plus pion field. This is essentially the product of scalar soft dilaton times U, this pion matrix. And I also introduce new baryon field, starting from this psi field appearing in nonlinear chiral Lagrangian times some function of Z. Okay? And now I can rewrite the nonlinear chiral Lagrangian in terms of now this new baryon field B and scalar field and pion field. So this scalar field is essentially a mixture of Q or tetrapole, whatever, any mesonic divisor which has the scalar quantum number and soft dilaton. And so this is the emergent linear sigma model Lagrangian. So this is essentially the same as the standard form of linear sigma model, but this potential term, this has the log term. This is coming from the dilaton potential. Okay, so this is an essential difference from the standard linear sigma model.
So where is the harder part?
Harder part plus harder part, of course, this should be added in the Lagrangian, but this has nothing to do with the chiral dynamics. So this is simply left over. So this full Lagrangian is those whole pieces plus Lagrangian for hard component. Hard dilaton kinetic term plus potential for hard component. So we assume there is no mixing between soft component and hard component. This is justified from phenomenological considerations. Okay, and plus some singular parts, singular contributions appear.
Sorry, say again what is the justification?
The solution of this dynamics is identified as such
Yeah, but that's what she wants to do. But if you start from the decomposition of the
Soft and hard.
dilaton, you are splitting dilaton into two pieces. Then you are splitting the field, not the, I guess, Lagrangian's.
That's right, that's true. So that's why I said we assume there is no mixing between soft sector and hard sector.
So that means that you are not actually splitting the just a field into two pieces.
Yeah, that's right. So that's why I wrote like that.
Right.
So this is the potential.
Right. So one should not think about this as chi is chi s plus chi h. So you are really introducing two independent
Lagrangian terms.
two scales.
Right.
So there isn't any point to consider that these and what the gluon condensation is sum of a soft part and hard part. There's no point to call it like that because
Okay.
you are really introducing two independent dynamics.
Right.
So it's just better to leave it as it was. One is chiral condensation, and the other one is the gluon condensation. Just
Then you
leave
will be in
it
trouble.
like that.
But there's a
The only thing you miss
but
there
no,
is
there's a
that you don't have a justification to use gluon condensation potential to as the chiral dynamics.
yeah, but there's a very deep argument by Freund and Lambo in 1970s who said that unless you have an explicit symmetry breaking, scale symmetry breaking,
Right.
you cannot have a spontaneous symmetry breaking in scalar symmetry. It's because the potential is flat, so nothing happens. So you need an explicit symmetry breaking. And the explicit symmetry breaking is done by the hard part. You need it.
I think his question is that anyway, we thought that the dilation is global.
Yeah. Right.
So now,
No, they are mixed. I mean, you know, the Russian sum rule tells you that the G square is related to also Q by Q.
No, but let me just say again what I'm saying.
Okay.
So my point is following. You want to introduce the chiral dynamics of potential, right? And you want to identify it as the global potential. However, all your treatment looks like such that the so-called the soft part and hard part is not necessarily just a piece of just the same thing. It's not like it. That's what I'm.
But she's using trace anomaly to start with.
No, and that is a kind of a deceiving thing.
No.
No, that's what I'm saying. You see,
The point
No,
of low energy physics.
let's-
Come on, wait a second. Wait. The point of low energy physics is that the scalar that we see in Valeska model is not Q by Q. But I mean that's how the whole thing started. I mean that's the mystery of the whole thing. It's not Q by Q. So we want to start something which is not Q by Q. That's what she's doing.
No.
Yes.
My point is that if you are really thinking about this is coming from the just one dilation, then you are splitting field. And if you keep that philosophy, then you should be consistent, right? On the other hand, the whole treatment here, it looks to me that you are not splitting dynamics from one field into two. You are not doing that.
So because so you are saying that the mixing term of soft and hard part should be there.
Should be there.
Okay, but if you have such a mixing, then you will be in trouble.
That's why I say that you are introducing two independent scalars. That's what I'm saying. Because there is no mixing between two split pieces. They are independent scalars, and therefore, the two part, there is no reason why two different scalars has the same potential form. Right?
Okay. I think this choice is not super unique.
Yeah.
Okay.
No, this potential is chosen in such a way that you calculate the dilaton current.
Yes.
Divergence of the dilaton current
there's
gives you the G square.
Right.
So that's all. That's all.
No, what I'm saying is this potential was calculated for this hard part, which has nothing to do with the soft part.
That's right. By definition, this is
so
our
the question
definition.
is why you want to use the hard part as a potential in order to discuss the soft part as the dynamics. That's,
But this is not done. She's not doing that.
No, this is the whole, what is the whole basis, I mean.
No,
Next,
I
look
think
at the-
I think I made this very clear. You need a explicit symmetry breaking in order to work with all these business that she is
I
doing.
don't think it's related to that.
Oh, it is. No, it is. I mean, it's. Okay, never mind.
Okay, so let me go on. Then we're going to make
So,
our discussion.
so
In the end.
may I ask single one further question? So, how many dilators do you have?
Single dilaton.
Only one.
No,
But it
I think
looks like-
she's actually introducing two
Yeah.
Ah, okay.
stellars and the
So,
discarded
how
one,
many
right?
independent
Other part is
degree of
discarded.
Yeah, this is the question.
Right.
And
And then-
then we are confused whether we have single dilaton or two independent dilatons.
Right.
That is.
If there is a single dilaton, there must be a mixing term. If there are
Right.
two scalars, then you are introducing the wrong, maybe, there's no basis to introduce this soft parts potential in terms of hard parts.
Well, you can think of this having two dilatons mixed together. Now, what we have is that at low energy, we integrate out hard dilaton because it's very massive. So you only look at the low one. But when you go to a regime in which the hard dilaton becomes relevant, that is above a TC, then it goes over to the other side. You can ignore it. So you have to go over there. But she's not doing that. She's looking at the low part, so she has to integrate out the high
Okay.
part. That's what it is.
Whatever, and she understood my question, so.
Yeah,
Yeah,
okay.
very good.
Okay. Okay. So when you apply this linearization, you will have additional terms which contains some inverse power of trace of sigma dagger. So this produces some singularities in chiral symmetry restored phase. So we would like to eliminate such terms, and these terms also carries parameters kappa and GA. Okay, and no singularities in this linear sigma model, our linear sigma model. This is guaranteed when you take those particular number for kappa and GA. GA, this is axial charge. So this is called dilaton limit. Okay. Yeah. So because those potentially singular functions are proportional to this particular combination of parameters. And when you require this coefficient becomes 0 and this coefficient becomes also 0, and then you have no singularity. And the theory, linear sigma model, is a well-defined framework, which is valid not only chiral symmetry broken phase but also in the restored phase. Okay, at the moment I have my ingredients are only pions and soft dilaton, scalar, meson, and nucleons. And now I want to introduce vector mesons. This is easy. So let me take hidden proximity Lagrangian. This is a nonlinear chiral Lagrangian for pion and omega and ground mesons. And also I consider two different assignments of nuclear chirality, naive model, standard model, and mirror models. And you can do the same things in the presence of ground mesons. This is not very difficult. And in addition to the previous terms, now I have new terms, those three terms associated with the presence of vector mesons. So V mu stands for rho mu or omega mu. Okay? And actually the dilaton limit in this case now, kappa is equal to 0, this is unchanged, and the GA is equal to GV. So GV, this is a new parameter associated with the vector mesons. And the requirement of no singularity is now required kappa is equal to 1 and GA is equal to GB, some number. And this condition, dilaton limit, is common to naive model or mirror model. And there is an argument by Weinbach using imposing rigid asymptotic behavior. This is a total angular momentum is proportional to Hadron mass squared. So he imposed this rigid theory into the argument of some current algebra in large MC limit, and then he got GA is equal to 1. So let's take this number, and then the dilaton limit is same as before. So GA is equal to GB is equal to 1. So what's the consequence? The consequence is vector nucleon interaction, which is repulsive. It takes the form G. This is a gauge coupling constant associated with vector mesons times this particular combination. One coming from covariant derivative, and GB is coming from some additional terms. And in this dilaton limit, this goes to 0, so this means vector nucleon repulsive interactions should suppress when the dilaton limit sets in. So this is an illustration of not only omega, so this is true not only for omega meson but also for isobector vector meson, raw mesons. So G vector nucleon coupling constant as a function of, say, density. Okay? And once the dilaton limit sets in, this vector nucleon repulsive interaction gets suppressed. And this is very small between dilaton limits and higher symmetry special point.
So could you explain what is low dilaton means?
So low dilaton means the dilaton limit sets in.
That's the
Okay, so below dilaton points, low dilaton, you can safely use nonlinear sigma 1. So here, the scalar sigma particle is very massive, so you can integrate it out. And now at this point, you have to switch from a scalar-less model to the model with scalars. So from nonlinear to linear. So the dilaton points is the point at which dilaton limit sets in. This is a sort of switching density or switching temperature of two different models.
So you say that all this change of dynamics of dilaton is caused by density.
Density is, yeah, of course this is driven by density or temperature, those external thermal parameters.
Is that the output or input? Is this assumption? Or
Eventually,
is assumption or this is something calculated?
you can calculate. It's possible to calculate this.
No, I mean the behavior of G omega n. So
This is a consequence.
This is a consequence.
Yes, this is a consequence.
But the assumption of there is a scale low dilaton by which dynamics is separated.
Right,
That is assumption.
right. This is assumption. Yes. Okay, so immediate application of this suppression of vector nucleon repulsive maybe softening of equation of states at high density temperature. So this is the pressure as a function of density. This is for neutron matter, not symmetric nuclear matter, but this is neutron matter. So those points, 3 points, are not direct data points, but they are extracted from 3 neutron stars in binary. And those points are compared to 3 theoretical lines. So essentially, those upper 2 lines in this calculation, so the people assume only nucleons as basic ingredients, no exotics. And this lower one, GS1, divided by GS1, here the cation condensation is assumed. And I have not plot here, but there is another plot in the paper. This is the relation of mass of neutron star as a function of radius. And on top of the observation and exotic scenario like a cation condensation of hot matter seem to be unpreferred. And the preferred scenario is the matter is still composed of very dense but still nucleons, ordinary hadrons. However, compared to those points extracted from experiments, seem to be a little bit too stiff. So what we need is the dense matter composed of non-exotic particles and non-exotic hadrons. Yes, we do have non-exotic hadrons. We have only standard hadronic diesel plus some softening of equation of state. So this can be described if we apply this linear signal model imposing chiral symmetry and trace invariance, because this requires the consequence of this model is that the repulsive delta-nucleon interaction should be suppressed. So this suppression gives you a softer equation of state. Okay, so now, so this is true not only for standard nucleons, but also true for mirror nucleons. So if mirror nucleon is realized in nature, so how large it is M0. So now I'm going to make a rough estimate of this M0. So now I have linear signal model, and one can easily construct Newton potential around the chiral symmetry restoration. So here, expectation value of S scalar field is very small. And positive and negative party nucleon mass is almost equal to M0. This is a common number. And the sublimate potential has a nucleon part plus, now this is the potential associated with hard dilaton. And a bosonic thermodynamic potential part associated with hard dilaton. Okay. This now I assume the same form for dilaton potential, hard dilaton potential, and associated mass, effective mass of hard dilaton. Okay, so to make a calculation, one has to fix those parameters appearing in the thermodynamic potential. And let's take chiral symmetry restoration temperature is roughly 170 MeV. We know it from lattice QCD computations, and take zero density, zero chemical potential. And we will have gap equation by minimizing the thermal potential with respect to chi H field, and this determines the expectation value of chi H hard dilaton field for a given M0. And also the mass, expression for mass for hard dilaton, this is also a function of chi H. Okay, and what we know from lattice QCD is this gluon composite operator at chiral symmetry restoration temperature is 1/2 of vacuum value, and from QCD summary calculation we roughly know the vacuum value of gluon condensate, which is given here, and from this we assume that the Mach constant associated with hard dilaton at chiral symmetry restriction temperature is roughly half of the vacuum value. And the vacuum Mach constant is is given, is known to be this number, more or less. And what about the mass of hard dilaton? So we identified a dilaton mass is just a glue ball mass, but it should be associated with hard component. And because of the same reasoning, coming from that hQCD observation, we also assume that this, so actually this is just proportional to B, okay, when you evaluate these derivatives. So we impose this dilaton mass square is also 1/2 of glue ball mass. This glue ball mass corresponding to the vacuum glue ball mass, say 1.7 GeV, which is heavy. And when you put those numbers into gap equations and this mass equations, you will arrive at some dynamically favored solution for M0 is around 200 MeV. Okay. So this is also consistent to all the estimate by Vitale and Chihiro done within the linear signal model, and also Longi made a calculation, so made an estimate of this M0 within a nonlinear signal model with hidden of symmetry but without dilatons. But he made a comparison of decay width and the pi nucleon scattering length in even and odd channel, and those external numbers are known, and he has been extracted a likely number for M0. This is pretty much consistent to 200 MeV.
Can I ask a question? So, is there any discrepancy or difference between the linear signal model prediction and the non-linear signal model prediction regarding this engine? Or
Discrepancy on M0,
Yeah.
no discrepancy.
No. So you mean that all this, there isn't any difference regarding this parity double?
Okay, there is still.
So when you take a different model,
Yeah.
then there is a discrepancy. But our conclusion is that, so this is our number because this is based on symmetry arguments, not specific model setup. So we prepare very basic ingredients, party double
So you mean
nucleons
M0
and mesons.
M0 is but what is the difference? What is the difference?
So for instance, the linear signal model without dilaton, which is applied to nuclear matter, the extracted value of M0 is 800 MeV, not 200 MeV. But we consider so simply their linear signal model, standard linear signal model is not applicable around the nuclear matter.
I see. So what you are claiming is that instead of 800, you have a 210,
Yes, 200 MeV.
which was the value of a nonlinear signal model. But here what it means, consistently that the Chihiro linear signal model.
Right, linear signal model, but they didn't have dilaton, of course.
Linear signal model, but they
Very
have,
standard linear signal model.
they have something else, right? Standard signal model, right?
No. Okay. Standard linear signal model means actually.
In terms of signal.
So they consider mirror nucleons. In this sense, this is not standard. But why I consider what I call it standard means they didn't impose scale invariance. So the difference is the potential for a sigma field.
Right. And you are using different
Yes,
potential.
I have log term. This is constrained by scale.
So I want to understand what is the this situation. You are using different linear signal model.
Yes.
And get the same in
Yes.
zero.
Yes.
And now why this is a surprise?
No, I just said this is consistent with known numbers.
No, but she's looking at near the phase transition.
That's right.
Yeah, they looked at in the vacuum.
Right.
Ah,
So
okay.
those numbers are
Yes, yes.
given in vacuum.
That's the difference.
So what do you mean by consistent? I mean, say you are considering different situations or based on different vacuum. So what the meaning of consistent? So are there any connections?
Because we consider this is associated with hard dilaton, which is nothing to do with spontaneous chiral symmetry breaking dynamics. So this considered to be, so this is likely that M0 is almost stable against T either mu.
So I would say that this usual so-called linear geometry is related to soft but not hard.
M0 is associated with hard
So
part.
actually, I would say that you are using the potential for hard part. And to me, it's kind of surprising that you get the same answer. But as Amanda said, that maybe you are looking at different regime. And so you don't need to be very happy or unhappy by having M0 the same value because you are using a different regime. So there's no reason why I'm not sure whether M0 is a vacuum value.
No, this is the value estimated at chiral symmetry resolution temperature.
So if, and that could be different at the vacuum, right?
Yeah, that's right.
So-
In general, it might be
So
designed.
it doesn't mean anything coincident, agree or disagree.
Why should it be different than vacuum? I mean, M0 is some constant.
Parameter of the theory.
It's a parameter of the theory.
Is it really a parameter?
Yeah, it's a parameter of
No,
the theory.
but I think that M0
No,
should be
no, no.
determined by the dynamics.
That's
Well,
right.
if
So
you- if
in
you
general,
can calculate, yes, more
M0 by itself
Yeah.
a function of T and density. Because this is effective theory.
No, but the
So
M0
this must carry some information of underlying dynamics.
yeah, it's okay. I mean, you can calculate the M0.
Yes.
It is given the M0. But the M0 is a part which should be very independent of
Right, because
very
we
smooth.
consider this is associated with hard component of
Yeah, it
dilaton.
doesn't change much.
Right,
That's
right.
the whole point.
Like that point.
Okay. So that's why it's
What's the shape?
so they have gotten 300 MeV for M0 and I have gotten 200 MeV, but I consider this is totally okay, consistent. So this is the meaning of consistent, okay?
I'm not so sure. I'm not so sure that one should talk about consistency with the Chihiro. After Chihiro just took a linear sigma model.
Yes.
Yeah, so why should it be true story in the vacuum other than what's good for? No, linear sigma model could be good for pi n scattering if you take a sigma mass very high and etc. Because that's non-linear sigma model. So here the linear sigma model is taken, and you look at the vacuum dynamics with the condition which is appropriate for the non-linear sigma model. So it should come out to be non-linear sigma model. So, and in that sense,
Yeah, so consistent with our number.
which is good news for Chihiro.
You mean that the value coming from Chihiro, it might be kind of the coincident by accident?
No. It's a linear sigma model. Linear sigma model applied to pi n scatterings and things like this. And you know, in the pi n scattering and things like this, you need a non-linear sigma model. So the sigma mass is very high and things like this. So it's okay. That's consistent with the sigma essentially current algebra argument.
Yeah, so this is just 3-level calculation.
Three-level calculation. So it's amazing that they are saying, that's what the.
By the way, does that depend on the details of the potential?
Yes,
Or
of course,
is it-
of course.
It is.
Right.
And the completely different when the potential gives the same answer.
I would expect
Which is weird.
M0 so there must be more or less similar number. Because as I said, scale anomaly is there everywhere.
They encoded the scale anomaly also.
Yes,
They did.
yes.
And what's the difference?
So the potential V and the scalar, that is not invariant on the conformal transformation.
Right.
So if you take that potential, then the divergence of the current is proportional to chi fourth, chi to the fourth. And then that's the right dimension for the G square. So that is constructed in that way. So this potential is supposed to represent the gluon condensation properly. So that's why they use this potential, this type of potential.
They also use the same potential?
Yes.
You will also use the same potential? So why what's the difference?
Same potential, but constant is different. This scale is different.
Yes. And with a different vacuum expectation value.
Right, that's
So
right.
I'm asking, if you are using the same potential, the same variable, then why you would?
No,
And with a different time, the
Yeah.
parameter, then why you get the same variable?
No, M0 doesn't depend on V.
So that's what I was asking.
Yes.
Does it depend on the details of a potential?
No. For this analysis for fine temperature, he just used some useful numbers at the chiral restriction.
So you are saying that it doesn't depend on the details of a potential?
Sure.
It's a parameter.
So she used just some values which is useful to calculate M0.
No, I'm now beginning to be confused.
I thought that the point of this story, one of the important points of the story is the assumption for usage of that kind of application. This was my understanding.
Yeah, I understand that part. I don't have any tendency to agree with that, but suppose this is the way to do it. And then what I didn't understand so far is I just want to see the difference between Chihiro and the U. And according to, I don't know, I didn't see any Lagrangian model, but the Young-Gil told me that the potential is the same but completely different parameter.
So to avoid the confusion, so let's first don't think about, let's just forget about this high temperature consideration. Let's consider only family rows. Zero calculation with the delta meter. That's much simpler. Right? Yeah. Zero temperature, that's the case. Yes. Then there is some difference in the model. So they give different M0.
Different M0.
Yes.
So this argument is just
270 MV.
Yes. And then what Chihiro was trying to tell you is that the number M0 can be inferred at the chiral restriction temperature. So that's what she's trying to tell you.
Okay, so you didn't say anything of the consistency or inconsistency. It's just a coincidence.
Yeah.
So the meaning is consistency. That's I don't know.
But the logic is somehow.
Yeah,
Yes,
I
yes,
think it's
yes.
consistent. No, I think it's consistent.
So basically, in your practice, you use the actual information.
Time scattering.
And that is like 870 or something.
Right. So if I get, say, 700 MeV, then I consider this is inconsistent, something is wrong.
And you consider only temperature around the chiral restriction. And M0 should be independent.
Later on.
And that is the value, that's the proof.
No, I mean the logic, I don't understand. I don't understand what. The M0 is the same business for everybody. Now, Chihiro, he writes a linear sigma model. And then he uses in the kinematics condition. I mean, linear sigma model, becomes non-linear sigma model when you let M sigma go to a very large number. Okay, so it's essentially at tree order they are the same. Because they're all working at a tree order. They are the same.
No, they're saying.
No. Let me continue. So what he's doing is, he says, okay, there are chiral doublets, and then you have M0s, and then I look at the interaction which occurs at t equals 0 and the density equal to 0. Now that means that the part which has to do with the pyramidion scattering and things, the normal part, the ordinary standard part, is same as essentially nonlinear sigma model. Okay? So there he then fixes this parameter M0, which appears because he introduces the entirely direct into the contribution sensor. Now, what she is doing is she's now introducing hidden local symmetry, which is equivalent to nonlinear sigma model, gauge equivalent, at t equals 0 and the density equal to 0. So they should be the same. Now, the thing which is interesting is, of course, that the M0 in this case is determined when the soft part disappears. Essentially, soft part evaporates, evaporates, and the harder part is there. And that's what she's using, the harder part. And that, so, in other words, there is an assumption which goes in, the potential is, there is no interference between two potentials. That's an assumption. And he uses several assumptions, and however, it's the same Lagrangian.
Oh, you say same Lagrangian is the same parameter. Huh?
Yeah, at the soft part, it's exactly the same. The low energy part. The low energy part.
No, linear sigma model and nonlinear sigma model they have different Lagrangian.
No, but
They are different.
what do you mean? Linear sigma model, the whole point is that linear sigma model, when you look at pi nucleus scattering.
The question is the apparent form is different. They are different.
Well,
Nonlinear sigma model is different.
Yeah, but scattering amplitude, for instance, this should be the same. This is low
The
energy
physical
theory.
quantity should be the same, but what?
No, when you compute, that's what Bentley did. All
If
this-
you are saying that everything depends on the low energy and the potential is irrelevant, then I'm fine. But if you say that, oh, potential is crucial and the potential is completely different and gives the same number, then I worry.
Okay. So strictly speaking, the potential is different because I have log, but when you expand near low density or low temperature, this is essentially the same.
So that means potential is irrelevant.
That's right.
Then if you say so, I have nothing to say.
Okay. Yeah, I thought that you were talking about this potential form of particle, not soft part. But soft, when you look at only soft part, the potential form is irrelevant.
In some sense, you justify your original assumption of state.
That's right. So I made a relation of this M0 to gluon condensation. So which is a more fundamental in the field. Okay? So I'm not dealing with M0 just as a parameter. Okay? So this is not a fitting. So what happened on other mesons within this framework, actually they are all becoming massless. Okay, so it's easy to generalize the hidden symmetry Lagrangian to in such a way that actual vector mesons are also incorporated, and so you can repeat the same procedure. And then now the mass term of the linearized Lagrangian has the terms associated with the mass of actual vector mesons and the mass of vector mesons, and they are determined by some A, C, and they are just model parameters, just number. But the important point is they are proportional to sigma condensation, the scalar condensation. So when the chiral symmetry is restored, they all vanish. So, but the question is whether this the manifestation of magnitude symmetry is preferred in this scenario or not. But necessarily maybe not. Just like the baryonic field, baryonic sector, it's possible to add like N0 term, which is kind of invariant mass term, also to the mesons. This is also a likely scenario. So that, but what we can learn from this is that the mass of vector mesons and in medium one meson mass and in medium A1 meson mass, they are all smaller than the corresponding vacuum values. However, they could stay some finite number even when the chiral symmetry is restored. Say another parameter for M0. So at the moment it's not clear how to make a relation. but it's likely that this M0 for meson is also associated with a non-vanishing gluon condensation. Okay, so this is my last topic. So about the phase diagram. So there are many scenarios on the phase diagram. So what happened on the phase diagram obtained from Sigma model in the presence of dilatons? So let me start with a very general thermal potential. This is for fermion part, nucleon part, gamma N, this is the degeneracy factor, and the part for dilaton and the corresponding potential. For sigma, this is responsible for spontaneous chiral symmetry breaking, and the chi, this is responsible for scale symmetry breaking. And if you parameterize the nucleon mass like this, so just so if G2 happening is 0, so this is just standard linear sigma model with nucleon. But I might also consider the possibility of a mirror scenario, and just for calculation and simplicity, I assume this kind of parameterization. So some part of nucleon mass is coming from sigma condensation, some other part is coming from expectation value of chi, dilaton, and this G2 times chi is nothing but N0, which we have been talking. And at the moment I didn't make any actual numerical calculations, but it's possible to see what's the likely and possible phase structure by looking at gap equations. So this potential, thermal potential, basically determines gives us two couple of gap equations, one for sigma condensation and another for chi condensation. And when you make some classification, then you will arrive at there are two possibilities on the phase diagram. This is phase diagram in T and mu direction, and the red curve corresponding to chiral symmetry restoration. And at say 0 chemical potential, there is a splitting between chiral transition and a sort of transition where expectation value of chi becomes 0. So chi is associated with gluon composite operator, so glue balls. So 0 expectation value of chi is considered to be a disappearance of composites, hadronic composites. So in this sense, this can be interpreted as a phase transition of confinement to deconfinement.
So the coincidence of the Ichiban and the chi vanishing point is an assumption?
No.
Or is
this is not assumption. So at 0 temperature, but at large chemical potential, two transitions happen simultaneously.
so why?
Because chi, this is boson, so this potential doesn't have any temperature dependence. This carries only temperature dependence and no density dependence at the level of mean field. So in that situation, okay, assume the chiral symmetry is already restored. So taking sigma expectation value becomes 0, and one of gap equation determines expectation value for chi, but this gives you only a trivial solution. Non-trivial solution.
So that means that sigma and
trivial solution.
sigma and chi dynamics is
Chi is 0, or chi expectation value is 0, or chi expectation value is same as vacuum one. Okay, so if trivial solution is chosen, then two transitions should happen simultaneously like that. But depending on the dynamics, it's also possible that the non-vanishing expectation value of chi is
so
chosen.
what is the what is the difference between the left and right? What is the difference? What parameter is different? in other words, what makes the 2-point and the same?
So the difference is the difference of the choice of the solution for the
Yeah, that's right.
equation for
So-
I.
So in general, okay. So in general, to sigma and chi of ceramics, but okay, assume chiral symmetry is restored. So let's take sigma is 0, and then I have only a single gap equation which determines the chi expectation value. In that situation, the gap equation is like chi some power of chi times log chi over chi 0 is equal to 0. This is the gap equation. In general, plus some other function, but this is a function of sigma. And when the chiral symmetry is restored, you have now these terms. So the solution is, of course, chi is equal to 0 or not equal to 0. So equal to chi 0. Okay? At t equals 0.
So you're saying that if chi 0 is
Mhm. If this is chosen, then this phase diagram is preferred. But if this non-zero value is chosen, then this is preferred. This depends on dynamics.
that means that it depends on the choice of chi 0.
Choice of the solution.
And the chi 0 is, although in fundamental theory may be dynamically different, but in your
Yes.
theory,
Mhm.
it is parameter right?
Mhm. But it's possible, of course, solve this dynamics because
So
this
that
is
means
mean
that
theory.
you are tuning, so in order to get this left hand side, you have to tune chi 0 equal to 0.
Yes, yes.
So which is impossible for your potential V, right?
Chi 0. No.
No.
Chi 0 is,
Different parameter than this.
this is non-vanishing everywhere.
So in that case, the right hand side is preferred.
Yeah, if this non-trivial solution is chosen, then this is preferred.
No, yeah, right. So in your model, you can't choose chi 0 equal 0.
Yeah, that's right.
Right.
Because I don't yet solve this dynamics. I simply made a possible classification of the phase diagram before making actual calculation because I don't like to make heavy calculation.
No, what I mean is that calculation is not based on your model, right?
No.
In your model,
This is something different.
right, choice of chi 0 is impossible to be sure.
That's right.
Okay.
That's right. Okay, so eventually, of course, we are able to know which is eventually preferred by the dynamics of this particular model.
And even before you begin any word, I begin to worry about things because in your model you cannot produce two different kind of phase diagram.
No.
Because
So
as
dynamics chooses one of them, of course.
that is impossible for you, I think, because as soon as you write down a Lagrangian chi 0 is non-zero.
Chi 0 is non-zero. Yes.
Right, as soon as you write down a Lagrangian.
Mhm.
So how can you reproduce the first one as a part of your dynamics?
I'm just keep worrying about the logarithmic term in potential.
Why?
If we put chi equals to 0, then the potential is infinite.
Right.
That's right.
That
okay.
not favor that
No chi
equation.
No, but chi is always multiplied in front of log, so this is
It's
0.
not zero.
If s is chi is 0.
Because the power of chi
Right here. Chi to the 4th log chi to chi is equal to
I
0.
have to study
Yeah.
the mathematics study.
Yeah.
Okay,
So chi times log chi in the limit of chi becomes 0. This is 0. Okay.
Okay.
And can you say something about the relation between chi and confinement to confinement? Because usually people say if confinement exists, then parasymmetry equation is right. But and so usually people draw the confinement line, and outside of that confinement line,
What is the in your case, pi is not directly related to finite.
No.
Indirectly, only indirectly.
Yeah, indirectly through the gap equation.
Okay, I think that I misunderstood your notation. So this chi0 is not the zero chi0. So this is expectation value. So forget it.
Hi.
So that's a mistake of notation.
Pi 0 at the blackboard is just
Expectation value. Expectation value. While here it's just a choice of normalization.
That's right.
That confused me.
Yeah, so this chi0 is determined from vacuum phenomena, like global mass or something. Okay, so this is my final slide. So I have listed several problems, issues to be understood. So the question is, the first question is, of course, at which temperature or which density the electron limit sets in. Okay? So for this, we have to solve the dynamics. And also, in general, there is a complicated mixing between all possible scalar modes, not only quaternion, but also tetra quarks and also gluons. They are all mixed in general. But increasing temperature or increasing density, there is a level crossing. And what we would have eventually is near the phase transition, only the quaternion component becomes the relevant, it should be lowest, because this eventually becomes chiral or pi. Okay, so this also related to some specific model dynamics and how to make a reliable estimate of M0 in dense matter. So I did an estimate at finite temperature but at zero density because we have some reliable input from lattice QCD computation, but finite density, as we know, there is no reliable lattice calculation for 3 colors. So the question is how to make it. And what's the phenomenal consequences on thermodynamics within this chiral trace anomaly imposed effective models. Okay, yeah, so that's all. Thank you very much.
Any further?
So I have one question about this. So Mendel's symmetry is derived using largest line. And in largest line, like quaternion and tetracopter, all components are does not mix. Because they are mixing with something.
That's right.
So actually, we have to choose one of them.
In largest degree.
Yeah. I can use Mendel's symmetry.
Well, I don't use medicine.
Yeah, so
And I will not take
different.
large MC.
Huh?
I will not take large MC.
Well,
Yeah,
in the Philadelphia limit, also simplifies when we use the RJC. So that limit of the
So this question is not directly.
But you see the second part, the mixed scalar modes, that's where Sangjin's problem actually takes place, because that means that the whatever scalar that you are having at low energy, there may be several scalars, and one of them it has something to do with the scalar anomaly and then the other excitations, and they are mixed. And therefore, when you write down this potential, that the potential is separate, so this is no function. There's no reason why they should be separate. So if you want to take into account all the dynamics, then you have to mix all of them in QCD language, all of them. And, you cannot do it. There's no way you can do it, so that's the point.
So one thing I didn't fully understand is number 3. It is why you claim that M0 is determined from the hard part. Could you say again why? I just missed it.
Because this is singlet under chiral transformation, so this is nothing to do with chiral, spontaneous chiral symmetry breaking, by definition.
I was maybe I didn't understand the soft part and the hard part splitting. So what is the definition of a soft part and the hard part in terms of this the chiral transformation? Are you saying that they are split according to the chiral symmetry behavior?
Well, both dilatons are of course singlet on the chiral transformation because this is gluon complex.
Right. Then you are the drawing
but the soft dilaton is of course kind of singlet, but the scalar modes appearing in our linearized model is actually a mixing of soft dilaton, soft glue ball, plus all other, say, QQ bar morphine.
Right. Then Y and M0 is depending only on the alpha.
Because this is surviving even when the chiral symmetry is restored. So this is only the scale when the chiral symmetry is restored. So,
but that scale, the thing which is confusing me is that the scale breaking is a sum of two pieces. So how can you say that the soft part is irrelevant?
Well, the scale symmetry can be broken. This is the argument which I studied. This is the argument by Freud and Number a long time ago. The scale symmetry can be broken both spontaneously and explicitly. So the M0 is essentially doing the explicit breaking, and then the spontaneous symmetry breaking is somehow tied to the chiral symmetry, so it disappears at the point where the Q by Q, the condensate
But I
was
think
released.
that harder part is also maybe could be spontaneous.
Oh yeah, well, because if you go to a higher scale, then that can also be treated as spontaneous. But it's a different level. So in terms of the scale, the soft part, the spontaneous broken symmetry, chiral symmetry, scale symmetry is in a sense restored at a scale which is lower than what would happen at higher. I mean, you're saying, okay, trace anomaly could be interpreted as some kind of spontaneous symmetry breaking at higher scale.
So I see what you mean. So what you mean is M0 is the vacuum parameter.
Yeah, that's right.
And things are running according to density, and maybe post-chiral, soft and harder part is changing at the moment where chiral symmetry is restored.
So
Where
the soft part, the soft part disappears, and then the hard part is there. Now, as she says, well, of course, M0 should depend upon the density and temperature. Of course, it should, but we should learn very smoothly at low density and low temperature.
But I think that at the place where you are working on, and it is at the density which is where chiral symmetry is stored, maybe this is correct. But at the vacuum, where both are non-zero,
that's right.
so it is not reliable, right? Therefore, you should say M0 is not the vacuum value, but the value at the chiral symmetry restoration.
Yeah, so in a sense, we have derived an effective theory which is valid only around the phase range.
Right. So M0 is not the vacuum value,
No,
but
no.
the critical value.
Right.
Good. I got you.
Okay, so everybody is happy now. Okay, but thank you.
Thank you very much.
Now it's lunchtime.
Thank you.